Wireless power transmission, also known as wireless energy transfer or wireless charging, is the process of transferring electrical energy from a power source to an electrical load without the need for a physical connection between the two. This is achieved by using electromagnetic fields to transmit power wirelessly over a short distance. The basic principle behind wireless power transmission is electromagnetic induction. When an alternating current flows through a coil of wire, it creates a magnetic field around the coil. If another coil of wire is placed nearby, and the magnetic field from the first coil passes over it, an electrical current will be induced in the second coil. This is the basic principle behind transformers, which are used to step up or step down the voltage in electrical power distribution. In wireless power transmission, the two coils are placed in close proximity to each other, and the power source is connected to the first coil. The electrical energy from the power source is converted into a high-frequency alternating current, which creates a magnetic field that is picked up by the second coil. The electrical energy is then transferred from the first coil to the second coil, where it can be used to power an electrical load. There are several different methods for wireless power transmission, including magnetic resonance, electromagnetic radiation, and microwaves. Each method has its own advantages and disadvantages, and the choice of method depends on the specific application. Wireless power transmission has several potential benefits, including eliminating the need for cables and connectors, reducing the risk of electrical shock and fire, and enabling the charging of devices in hard-to-reach places. It has applications in a variety of industries, including consumer electronics, healthcare, automotive, and aerospace. Let me explain several types of wireless power transmission technologies available, each with its own unique characteristics and advantages. Here are some of the most common types. Magnetic resonance. This is a more advanced form of inductive coupling that allows for greater distances between the two coils. It involves using resonant circuits to match the frequency of the power source to the resonant frequency of the receiver coil, which improves the efficiency of power transfer. Radio frequency, RF, wireless power. This technology uses electromagnetic waves in the radio frequency range to transfer power wirelessly. It typically operates at higher frequencies than inductive coupling, allowing for longer distances between the transmitter and receiver. Laser-based wireless power. This is a relatively new technology that uses lasers to transfer power wirelessly. It involves converting electrical power into a laser beam, which is then transmitted to the receiver where it is converted back into electrical power. Microwave-based wireless power. This technology uses microwaves to transfer power wirelessly. It typically operates at higher frequencies than radio frequency wireless power, and can be used for longer distance power transfer. Each of these technologies has its own advantages and disadvantages. Inductive coupling is the most widely used and has a proven track record of safety and reliability. Magnetic resonance offers higher efficiency and longer range, but is more complex and expensive. RF wireless power has potential for long-range power transfer, but faces challenges with interference and regulation. Laser-based and microwave-based wireless power are still in the early stages of development and have potential for high-power applications, but may face challenges with safety and regulatory approval. Wireless power transmission offers several advantages over traditional wired charging methods, but also has some disadvantages. Here are some of the key advantages and disadvantages. Advantages. Convenience. Wireless power transmission eliminates the need for cables and connectors, making it more convenient to charge devices. Safety. With wireless power transmission, there is no direct contact between the power source and the device being charged, reducing the risk of electrical shock and fire. Flexibility. Wireless power transmission can be used to charge devices in hard-to-reach places, such as inside sealed electronic devices. Durability. Wireless power transmission eliminates the wear and tear on charging cables and connectors, which can wear out over time and need to be replaced. Efficiency. With some wireless power transmission technologies, such as magnetic resonance, the efficiency of power transfer can be higher than with traditional wired charging methods. Disadvantages. Efficiency. Some wireless power transmission technologies may not be as efficient as traditional wired charging methods, resulting in longer charging times or lower overall power output. Range. The range of wireless power transmission may be limited compared to traditional wired charging methods, particularly for high-power applications. Cost. Wireless power transmission can be more expensive to implement than traditional wired charging methods. Interference. Some wireless power transmission technologies, particularly RF and microwave-based methods, may be more susceptible to interference from other electronic devices. Standardization. There is currently no widely accepted standard for wireless power transmission, which can create compatibility issues between different devices and charging systems. The maximum distance over which wireless power transmission can effectively transmit power depends on the specific technology being used. Generally, wireless power transmission is most effective at short distances, typically a few centimeters to a few meters. However, some technologies can transmit power over longer distances. Inductive coupling, which is the most commonly used wireless power transmission technology, is typically limited to distances of a few centimeters to a few inches. This is because the magnetic field created by the transmitter coil weakens rapidly with distance, and power transfer becomes less efficient as the distance between the transmitter and receiver increases. Magnetic resonance technology can transmit power over longer distances, up to several meters. This is because magnetic resonance uses resonant circuits to match the frequency of the power source to the resonant frequency of the receiver coil, which improves the efficiency of power transfer and allows for greater distances between the transmitter and receiver. RF wireless power and microwave-based wireless power technologies can transmit power over even longer distances, up to tens of meters or more. However, these technologies are less efficient and more susceptible to interference than inductive coupling and magnetic resonance technologies. Overall, the maximum distance over which wireless power transmission can effectively transmit power depends on the specific application, technology used, and desired level of efficiency. Wireless power transmission can impact battery life and performance for devices being charged in several ways, depending on the specific technology used and the implementation details. Here are some of the key factors to consider. Heat generation. Wireless power transmission can generate heat in the device being charged, which can reduce battery life and performance. The amount of heat generated depends on the technology used, the efficiency of power transfer, and the power output. Charging speed. Wireless power transmission may not be as fast as traditional wired charging methods, which can impact the performance of the device being charged. The charging speed depends on the technology used, the power output, and the efficiency of power transfer. Efficiency. Wireless power transmission may be less efficient than traditional wired charging methods, which can impact battery life and performance. The efficiency depends on the technology used, the distance between the transmitter and receiver, and the power output. Battery compatibility. Some types of wireless power transmission may not be compatible with all types of batteries, which can impact battery life and performance. For example, some technologies may be better suited for charging lithium-ion batteries than other types of batteries. Battery health. Wireless power transmission may impact battery health over time, depending on the specific implementation details. For example, if the device is left on the charging pad for an extended period of time, it could overcharge the battery and reduce its overall lifespan. Wireless power transmission technology is being used in a variety of applications across different industries. Here are some of the current applications and industries that are exploring the potential of wireless power transmission. Consumer electronics. Wireless power transmission is commonly used in consumer electronics such as smartphones, smartwatches, and wireless earbuds. Some products, like wireless charging pads, are also available for home and office use. Automotive. Wireless power transmission is being explored as a potential charging method for electric vehicles. This would eliminate the need for physical charging cables and could make charging more convenient for drivers. Medical devices. Wireless power transmission is being used in medical devices such as implantable pacemakers and hearing aids. This eliminates the need for battery replacement surgery, which can be risky for patients. Industrial automation. Wireless power transmission is being explored as a potential solution for powering sensors and other devices in industrial automation applications. This would eliminate the need for wiring and could reduce maintenance costs. Aerospace and defense. Wireless power transmission is being explored as a potential solution for powering unmanned aerial vehicles, UAVs, and other types of autonomous vehicles. This could eliminate the need for physical charging cables or onboard batteries, which could increase the range and capabilities of these vehicles.